welcome everybody. So today we are going to discuss about quantizing scalar fields. And for this lecture, actually I am considering that the audience knows about what is a Hilbert space and what is a Fock space. If not, then you may refer to the previous video in this channel where we have discussed how to come from Hilbert space to a Fock space. So essentially we are talking about quantizing a system with many degrees of freedom, preferably infinite degrees of freedom. What I mean by that, I cannot go into detail in this lecture. You might see the previous lecture. So in classical mechanics, we know that there is something called Lagrangian and there is something called Hamiltonian. So we write down a quantity called action like this. It's a time integral of a function which is called Lagrangian, and this function depends on variables q, q dot and t, where q is usually the position, but it can be the angle. So in general it is called a generalized coordinate. Q dot is the time derivative and of this position, and this is the familiar velocity for us, and t is the time. So this quantity action is said to be containing all the information about the dynamics of the system, and I hope the audience knows how to arrive at the dynamics. The dynamics is arrived by taking variation of the action and setting it equal to 0, which is the famous action principle, and you know that if you do that, you will arrive at something called Lagrange equation of motion, which is d dt of del L del Q dot, which is equal to del L del Q. So these are partial derivatives because the Lagrangian L depends on variables other than Q dot in this case. So if you vary with Q dot, you have to take a partial derivative. Same logic goes when you take a variation with respect to Q. So this is the famous Lagrange equation of motion, and I hope everybody knows about it. And from this, now one can define something called the Hamiltonian, which is obtained through a Legendre transformation from the Lagrangian like this, where this small p is the momentum, and the momentum is defined as the derivative of Lagrangian with respect to the velocity. Okay? And after that, one can arrive at the Hamilton's equations, which are okay. So one can take a particular example for say the free particle or the harmonic oscillator to check that the Lagrangian description and the Hamiltonian description are completely equivalent. So this is the story of a single particle, actually, because P and Q belong to a single particle. So what will happen if you have more than one particle, say many body particle, say n particle system. Then this whole thing generalizes to say we have Q1, Q2 up to Qn, then sorry, q1 dot, q2 dot up to qn dot and then time. So everything looks the same, just you have to put certain indices that for example the Lagrange equation will become del L del qk dot is equal to del L del qk, which is for every k that belongs to the set 1, 2 up to n. Similarly, we will have for the Hamiltonian system minus pk dot, and the Legendre transformation that relates Hamiltonian and Lagrangian, it will have a summation and everything else remains the same. So essentially you can see the one particle dynamics is repeated for each value of k, and even the Legendre transformation we do it for each and every k. So you go to a many particle system and you go on. But the problem arises when you have infinite degrees of freedom of the system. I am talking about a field. If your dynamical system is a continuous system, which definitely have infinite degrees of freedom, this will vary not only over space but also over time, and it will be an extended object. Because of this extended object nature, what will happen that you cannot ascribe a particular position to this field. It will have many different positions because it will exist at different positions at a given time. So what to do? For this case, we have to modify our notion of Lagrangian or Hamiltonian. So in this lecture, I am trying to avoid any kind of mathematical hand waving, but I cannot spend much time in every detail. So please follow it up judiciously, I would say. So in case of a field, now you can write the action as a time integral of the Lagrangian, but this Lagrangian itself, you write it as a space integral, which I am considering a d-dimensional space in general. You can take d is equal to 3 for real physical space of a Lagrangian density. We will be talking about densities more because it's a continuous system we are considering now, and this Lagrangian density will not depend on individual positions and momentum because frankly there are infinitely many. Rather, it will depend on the amplitude of the field, which is phi, which itself is a function of space and time. Then its time derivative, which is dot space and time. Then again this field, unlike position, it varies over space also. So space derivative of this field, and finally time. And please mind it that this phi dot is now not a total derivative, but it is a partial derivative with respect to time of the field, because the field itself depends on position and time. So, with this definition of the Lagrangian, we see that the actual dynamical variables are field amplitude phi, and what we will be integrating over is over the coordinates x and t. So, the left hand side definitely will not depend on x and t, they are integrated out, but the left hand side will depend on the field amplitude phi and phi dot and other quantities. So, in general, action is called a functional of the field variable. It is not a function because there are time and space integrals performed already, but it is a functional. It depends on the form of the function. Okay. So, now in this language you can now construct a Hamiltonian H through a functional Legendre transformation, which is phi, and if you remember the definition of momentum, we write it like this. Sorry. Minus the Lagrangian density. Okay. And it is customary to write the momentum corresponding to this field variable as pi. Okay. So, Hamiltonian itself will only depend on time because the space is integrated over. So, in that sense, Hamiltonian is also a functional of phi, but it depends on time. So, at this level you can see, if I am defining a Lagrangian density, automatically I can define a Hamiltonian density, which will be this, and that usually is labeled as curly H. Okay. So, now the equation of motion for the field system changes a little bit, although the general principle is always this, that the variation of the action vanishes for the physical process. If you do that, you see that in terms of the Lagrangian, or rather Lagrangian density, we can write down this as del L del phi of delta phi plus del L del phi dot delta phi dot plus del L del k phi delta del k phi. Okay. So, k is the individual label for the dimension. So, in a d-dimensional space you have to consider from k is equal to 1 to d. So, that many different derivatives are there. So, you have to consider all of them. So, I am just using the chain rule for differentiation, nothing more. The next thing you have to consider is that this variation delta is arbitrary. So, for any operator like time derivative or space derivative acting on a field, if that quantity if you consider the variation of this, then you can very much take the derivative outside of the variation. That means this is equal to delta phi. Remember, I am considering a variation which is totally arbitrary. If this variation depends on space and time, etc., then this is not true. And then after taking the derivative outside of the variation, this term and this term will have a derivative outside, and using the concept that the variation of this whole system vanishes at the boundary, which is a core principle of Lagrangian principle, we can shift the total derivative so that the time derivative here moves to this term and the space derivative here moves to this term. So we can write down, sorry, this was is equal to 0, this whole equation as, so I am already going into space-time notation, so I am writing d plus 1, but do not consider that this is a relativistic system, I am just taking a notation. So this I can now write as del L del phi minus del T of del L del phi dot minus del K summation over K del L del K phi delta phi is equal to 0. And because now delta phi is common and it is totally arbitrary, the most general way that this whole integral can vanish, that this square bracket will vanish, and that will give you the Lagrange equation for the field phi, which just looks like this. Okay. So you immediately notice one thing, that I did not mention anything about the symmetry of the space-time of this system, whether it is non-relativistic or relativistic. I just considered a general Lagrangian, and in this equation you can see the space derivative term and the time derivative term are considered at the same footing. So that means space and time are mathematically equivalent, just that space degrees of freedom are more than 1 usually. So this is the reason we call the Lagrangian formalism to be inherently covariant. And usually when you have a relativistic theory like Klein-Gordon model or say Dirac theory or even the Maxwell's theory, we usually go to Lagrangian formalism to handle it directly, because there is explicit covariance and it helps you to have consistent mathematics very easily. But that is not necessary, you can very much do the Hamiltonian formalism, and in some cases to find out the physical degrees of freedom when there are constraints, usually Hamiltonian approach is better. So it's a give and take game. So now let's come to the portion of quantization, and desperately I choose a Schrodinger field Lagrangian. The reason behind is that usually in field theory courses people are taught that the simplest case is the Klein-Gordon field, which we will come to discuss later, but that is not true. Even you can have a field theory with a Schrodinger kind of non-relativistic setup, because many systems in physics like superconductivity, coal atoms, etc., low energy systems, the field systems considered corresponding to those systems are actually non-relativistic, and they give important phenomena like superconductivity and Bose-Einstein condensation, etc. So it is instructive to do a non-relativistic field theory or field quantization, at least to start with, so that you understand the notion of field quantization independent of any non-relativistic or relativistic bias. So the Schrödinger field and the Lagrangian density for this case is given as this. I hope people are familiar with these notations. So psi is the field variable, and these are the time derivatives. I am considering a Laplacian here in d dimension. You can consider it to be in 3 dimension, and the potential V, it depends only on position. But be careful, if I am calling it a Schrödinger field, this does not mean it is a quantum mechanical wave function. I am just writing down a Lagrangian density of a field. So for me, as of now, phi, psi are classical field variables. So simply psi depends on space and time, that is it, nothing more than that. Secondly, psi and psi star are independent variables, in the same sense that a complex number is independent of its complex conjugate. So please keep that in mind. And how to construct this Lagrangian? Okay, honestly speaking, constructing a Lagrangian is a bit of a trial and error process, because the physical object you strictly observe is the equation of motion, and we know what is the Schrödinger equation of motion. You can arrive at it by taking the variation following the Lagrange equation, which is, as we said, will be like this: k is equal to 1 to d del ls del k psi is equal to del ls del psi. You just plug these values in, and I am just writing the equation for psi as of now. So you will arrive at the equation, which will be actually minus I h bar del t psi star is equal to minus h bar square by 2m psi star. Okay, you can check by replacing the quantity. Just you have to keep it in mind that for some cases you have to shift a total derivative, because this particular term has a double derivative over psi, which is absent in the Lagrange equation, but it is totally allowed to shift a derivative to psi star, because we are in the domain of action principle, where the fluctuations on the boundary vanish or variations vanish. So if you vary the Lagrangian with psi star to find the equation, it is actually very easy to read off from the Lagrangian, which will only be I h bar del t psi is equal to minus h bar square by twice m Laplacian Vx is equal to psi. So, the two equations are essentially the same because one is the complex conjugate of the other. But what I was saying that this is the physical quantity that gives you your observable dynamics. So, the Lagrangian is obtained by arguing that varying this Lagrangian you can arrive at the equation of motion. So, this is a Lagrangian which actually gives you an equation of motion like this through the Lagrange action principle. So, this action works, but to construct this action from the first principle, it's not very impossible. What I am saying that it's a little bit involved, that usually if you compare the Lagrangian for a simple particle, it is some q dot square by 2m plus v which depends on q, sorry minus that depends on q. So, from there how you arrive at here, actually I was talking about that in my first video in the sense of Hilbert space to Fock space transition. So, if you introduce field variables, you cannot talk about these q's, the positions, you have to talk about the fields as I said, and for that you have to generalize this quantity a little bit, and that generalization for a non-relativistic system is simply this much. So, I hope students can read up a little bit on this. So, let us go forward. So, we have a Lagrangian and we have an equation of motion, but this is not quantized yet. In some sense it is still classical. So, to quantize it, let us consider this operator to be small h, and if you notice from your knowledge of Schrodinger equation, this is the Schrodinger equation, we call this operator as the single particle Hamiltonian, and this operator is Hermitian, that it is its own Hermitian conjugate, and because of this property, if you have a basis for this operator or the eigenfunction of this Hamiltonian, they will form a complete set. So, the eigenfunction, if I define it like this with En be the eigenvalues, these UNs form a complete set. That means that they are orthogonal. So, one means this, and this scalar product is taken against a norm which is defined in a complex space which is actually the Hilbert space. That is why this star will come in. You know, I expect you know it from your knowledge of quantum mechanics, and also that they satisfy completeness condition also, that we get a Dirac delta, spatial Dirac delta, when we just consider this quantity, this combination. So, these two conditions will be used because it is a complete basis, single particle basis, to find out further results. So, from there we can immediately say that this Schrodinger field psi, it is a linear combination of this single particle wave functions. That means this psi can be written as some n going from 1 to infinity, some a n of unx. Okay. Now the thing is that unx are eigenvalues, eigenfunctions of a Hamiltonian, and this Hamiltonian, single particle Hamiltonian, does not depend on time, as we know. So it will depend, these eigenfunctions will depend only on position, but we know this psi depends on both position and time. So the time dependence can come from only one place, that these expansion coefficients have to be time dependent. Okay. So if you just consider that, then we can write down the Lagrangian that we wrote earlier. We wrote the Lagrangian density, so the Lagrangian will be d dx of Lagrangian density. So d dx psi star I h bar del t of del t plus h bar square twice m square minus v of x psi. And now we will just substitute psi and psi star from this expression, if you do that, then just you need to substitute these quantities here and here. Just be careful that don't mix up the indices, because there will be an expansion for psi star which will correspond to, say, index n, and there will be an expansion for psi which will correspond to another index, but you should not mix it up with the index for psi star. So you have to give two indices, and that's why it can be written as a double summation, both goes from 1 to infinity, n star d dx um star un dan dt minus an h un bracket close. Okay. So you can see all these operators. So I am taking the shorthand that this is just minus of h. So all these operators acts on psi, and psi is expanded with the index n here. So d dt acts on an, and h will act on un only. So the expansion coefficients or expansion terms for psi star will not get affected by the operators. You just follow that consistently and it will just come on. And then what you can write down, that this h acting on un, you replace it from this eigenvalue equation. So it will be just a constant value en standing in here. Okay. And that means from both the terms you can take un out. So if un comes out from here, so we can write it here. We can use the completeness condition, or rather we can use the orthogonality condition, and this whole integration, which extends only to this part, will give you a Dirac delta. And applying this Dirac delta, we can get rid of one of the summations. Say we get rid of the m summation, and this m index will become n. So finally you can write it down, the whole thing, as summation over n is equal to 1 to infinity a n star I h bar a n dot minus e n a n, just that much. And let us call the thing inside the summation to be some L n. Okay. And although not clear from a classical picture, this quantity inside the summation, this Ln, is essentially a single particle Lagrangian. But the variables here are no more some space-time variables. This Lagrangian does not depend on space and time, rather it depends on these coefficients, time-dependent coefficients an and the eigenvalue En. So this is possible only in the quantum picture. That's why it doesn't look like anything which we know from classical mechanics. But more importantly, these ANs will soon turn out to be operators in the Fock space or the space, vector space for quantized fields or second quantized vector space. So then this Lagrangian, individual Lagrangian Ln, will be known as the Lagrangian for single particle excitations in the Fock space. We will see that. But before that, similarly, if you consider the equation of motion, then equation of motion had a form like I h bar del p psi is equal to, I am using the notation small h Hamiltonian like this, and this equation of motion, if you do the same thing, you substitute the summation for psi, it will just give you I h bar a n dot is equal to E n a n. Okay, and you can take its complex conjugation to arrive at the equation of motion for psi star, but essentially they have the same information. And from here you see one thing, that these ANs are classical numbers till now, although they come from a Schrodinger equation, single particle Schrodinger equation, which is a quantum system, because we have gotten rid of the basis which was actually quantum in nature. So in that sense we again arrive at a classical part, but mind you, it is a first quantized entity because it comes from a Schrodinger equation. So fine, we can define a momentum operator also, considering this Ls, and that momentum operator is simply pi n is equal to, by definition, partial derivative of Ls with respect to a n dot, where we are considering a n to be the dynamical variable, which is the only available quantity now, and you will find it to be I h bar a n star. So essentially you can see this a n star is a canonical conjugate of a n. So they form a canonical pair. But the momentum corresponding to a n star is 0, because the Lagrangian does not depend on a n star, a n star dot rather. But that actually does not mean that there are redundant degrees of freedom, as we know from constraint systems, because you can actually write this whole Lagrangian symmetrically in terms of psi and psi star by shifting total derivatives. So that is also done. So for now we will say that we will just consider this part, and that is our momentum, and an are the coordinates, equivalent coordinates. So if you have the information of momentum and coordinate, you can write down the Hamiltonian of this system, and that will be Hs, which is equal to n summation pi n a n star dot plus pi n star a n star dot. Remember, you have to consider all the different variables, and because a n and a n star are complex conjugate of each other, they are linearly independent, and that's why you have to consider them separately when you do the Legendre transformation. This thing, and minus Ls, and particularly for this case pi n star is 0, and you put I should write n or s, this is s, this is Ls, yeah, fine. So the Hamiltonian, total Hamiltonian we are considering, and finally doing this, if you substitute Ls, which is here from the expression for the Lagrangian, you finally end up with something which looks like En, An star, An, and that is very important. First of all, note that in both the Lagrangian expression now and the Hamiltonian, there is no integration, there is only summation. So somehow, first of all, we are not in the coordinate space, we are in a different space where there is a summation, but this summation is an infinite summation, obviously. Secondly, each mode is separated, and for the individual mode, you have the energy multiplied with something, and the thing inside, let me call it Hn, like I introduced Ln before. So all this Ln and Hn belongs to a particular n. You can consider it to be a particular degree of freedom, and for that you can have individual dynamics, because n is equal to 1, 2, 3, 4, they are not connected with each other, they are totally separate, it is a summation. That already gives you many hints about the vector space I am talking about. So finally arrive at the vector space, I have to now quantize the system, and how to quantize? It is very simple, that these classical coefficient functions ans or an star, just upgrade them to operators. And what does the operator do? The operator have non-trivial commutation relation. So we postulate a commutation, a canonical commutation, that an does not commute with its canonical conjugate, but it is I h bar delta mn, and putting the value of pi m, which is I h bar m star. So we have an, am, but instead of star I am going to write dagger is equal to delta mn, where I have considered this pi m is equal to I h bar am dagger. So I have replaced the star complex conjugate with dagger Hermitian conjugate. Why? Because a complex number will never satisfy a commutation relation like this, because they will always commute. So only way it is possible, and that is the crux of quantization, that you upgrade your variables to operators and define non-trivial commutators. So this is our operational commutator now, and from here you can see the Hamiltonian I can write down as this. Okay, now I would say the second quantization is complete, And where have you seen this object before? This is nothing but the harmonic oscillator Hamiltonian. The structure is the same, but the only difference is that we have not given any structure, internal structure of these AN operators, but in harmonic oscillator you know they are linear combinations of position and momentum operators, right? But at least for this structure and from this commutator is exactly the Heisenberg algebra or harmonic oscillator commutator relation. From there you know for each n it depicts a Hilbert space which is equispaced, okay, and it is from this commutator itself. This commutator will give you a Hilbert space which is equispaced with a gap which is 1 and 1. Actually I have considered the unit system for which actually this has to be h bar omega in terms of harmonic oscillator language, but this gap is 1 if you use this commutator. Remember your harmonic oscillator mathematics. So these gaps are equal, and the lowest value where n the lowest energy eigenvalue, this will have a width half or half h bar omega in the language of harmonic oscillator. So this will automatically will come, so equispaced levels and all, and these levels will be infinite in number. So for each AN you have, or each species for n is equal to a particular value, you have infinite energy levels, but each AN corresponds to a particular solution of the single particle Schrodinger equation. And how many solutions were there? Obviously there were infinity, as we checked before, because n goes from 1 to infinity, and for each mode you have again infinite levels. For each n you have infinite levels. So this is the second quantization, that these comes from a first quantized system, these ANs, and you quantize them again. And the vector space you get, that for each AN you have infinite tower of equispaced energy levels. This is the Hilbert space. Oh, this is, sorry, not the Hilbert space. This is the Fock space, which is kind of can be thought as a combination of individual Hilbert spaces for each mode represented by n. And you can see that this is harmonic oscillator, and when you will do scalar field theory, which you will do again relativistic Klein-Gordon scalar field theory, you will arrive at the same structure, identically the same structure finally, although the path may be a little bit different. It will have the same structure for the Hilbert space. But Schrodinger case is a non-relativistic field and Klein-Gordon case is a relativistic field, but we end up with a harmonic oscillator Hilbert Fock space anyhow. So this formulation itself is independent of whether you are from a non-relativistic background or from a relativistic background. It will give you a Fock space that depends on a Heisenberg algebra, and this is true for any non-interacting theory. Like you have a many-body system which does not interact among itself, you will always end up with a harmonic oscillator like Fock space. And for the states in this Hilbert space, or rather Fock space, it will be a tensor product of individual Hilbert spaces corresponding to each value of n, and there will be infinite of them, and each individual Hamiltonian will act on this individual Hilbert space to yield a contribution to this term. And just for completion, the quantity an dagger is considered the number operator, as you know from harmonic oscillator. Okay, I won't go further regarding this topic. I hope to introduce relativistic scalar field or Klein-Gordon field in the next lecture. But before that, just something about these operators. So because these AN operators, they depend on time, they must have time evolution, and classically or at the level of Schrodinger equation, which is in terms of this quantity AN look like this, you just can integrate and it will simply give you that ANT is equal to AN at 0 e to the power minus I ENT by h bar, which is the famous unitary time evolution of any quantity in quantum mechanics. But now, because these ANs are no longer functions but they are operators, we have to follow the Heisenberg equation, which I will just introduce, that IH bar DAN. I am using a hat to denote operator now, and it will evolve in terms of individual Hamiltonians. I should write HN, AN dagger, where HN is nothing but EN, AN dagger, AN, and this quantity I do not need to state specifically for the solution, but this solution will now look like that ANT is equal to e to the power I HN T by h bar, the operator at time t is equal to 0 minus I HN T by h bar. Okay. So this is again a unitary time evolution, but that of the operator. And here the inherent assumption is that the Hamiltonian does not depend on time. Otherwise, there will be integration over time in the Hamiltonian. And how to arrive at this, I told you that I will not do much hand waving, but it's a simple but tedious calculation that you take this equation and you write it down as, which you can very easily do. Yes, you just shift the derivative to the other side and take an integral, and from this side we have AN of t is equal to AN 0 plus 1 over I h bar 0 to t HN AN. So actually this is not a solution, you see the commutator again appears, but the trick is to replace iteratively this AN with this whole expression. So write instead of this AN, this whole expression for ANT inside, and if you keep on doing that, you can keep on doing that term by term again and again. Then after some manipulation, it can be shown, basically you have to introduce time order products because there will be integration over different time variables, and you finally have to use the Baker-Campbell-Hausdorff formula after this time ordering T. So basically you do time ordering first, then BCS formula second, you will arrive at simply ANT is equal to this expression we had before. Okay. So I just stop here. Before saying that, just if you apply the expansion for the wave function, you can write down also that if you upgrade the wave function to the operator again, just using the expressions we have at equal time, you have this to be a Dirac delta function. Y, sorry, this is y. So the wave functions are also they satisfy a equivalent algebra, but this psi serves as amplitudes in the Fock space and also in the old Hilbert space of Schrodinger equation. Just remember that psi is a connection between second quantization and first quantization for now, and that's why this psi is usually called a mean field description of the second quantized system, which gives you a effective theory. For us, the interesting thing is now that if you keep on applying operators on this Fock space in the individual harmonic oscillator Hilbert spaces, it will give you excited states which will correspond to number of excitations, or rather photons, from the harmonic oscillator concept. These are actually Fock space photons, but they are not actual photons. But in general, they represent something which is not seen classically, because classically these ANs were only some parameters. That means they did not have infinite number of excited states or something like that. So what these excited states mean, and that is a story for relativistic systems, that we see more and more particles popping out when you have high energies in the system. So particle creation and annihilation are represented essentially by these Fock space operators, and that becomes interesting only in the relativistic systems, because non-relativistic system we never have particle creation or absorption. So that we hope to discuss in case of scalar field theory. Thank you.